Since we know we can use row operations to solve systems of linear equations, let's try out that technique on a couple different systems of linear equations. Let's solve this one. So maybe the first thing to do would be to take the second row, right? We already have 1 times x in this upper left-hand position. So let's take the second row and zero out the x's by adding 2 times the first row. And also we can take the third row and subtract the first row. And that'll zero out the x's there as well. So our first equation isn't changing. X plus 3y minus z equals 2. And our second equation, so we need to add 2 times the first equation. So minus 2x plus 2x is no x's. Minus y plus 2 times 3y is 5y. 2z plus 2 times negative z is minus 2z. So total, that's 0z, so no z's, equals 7 plus 2 times 2, so 4, so 11. Okay, and now we'll take our first equation and third equation and subtract the first equation. So no x's, 5y, no z's, and then 13 minus 11 is, 13 minus 2 is 11. Okay, well, this is looking a little strange because, well, I guess it's kind of strange that the z's disappeared, but also the last 2 equations are actually the same equation now. So what does that mean? Well, let's continue doing what we usually do and, finish zeroing out the next thing we would do is use the y's in this position to zero out the y's that are below it. So let's do that. So we could take the third row and subtract the second row. So that's not going to change the first equation. So x plus 3y minus z equals 2. That doesn't change the second equation. So 5y equals 11. But it makes the third equation 0 equals 0. So now the third equation, this is always true, right? It doesn't matter what values you choose for x, y, and z. So 0 is always equal to 0. So this third equation isn't actually giving us any information. It doesn't really say anything about what x, y, and z are supposed to be. Okay. But still, what does that mean? Well, let's continue solving this in the usual way. At this point, what we would normally do is back substitute. So let's finish, I guess we need to still finish solving for y. So y is 11 over 5. And now we can use this to back substitute. We get x plus 3 times y, which is 11 over 5, minus z equals 2. So this gives us, let's see, x plus 33 over 5 minus z equals 2. And then we can move the 33 over 5 to the right. So x minus z equals, let's see, 2 is 10 over 5. Minus 33 over 5 is minus 23 over 5. Okay. So x minus z is minus 23 over 5, and y is 11 over 5. All right. So this first result here, we can sort of view this as saying something about x, or we can view this as saying something about y, or I'm sorry, saying something about z, just depending on whether we solve this equation for x or for z. And it looks like solving for z is going to be straightforward, so let's do that. So we get x equals minus 23 over 5 plus z. Okay. So now when we write down our solutions, right, we need to say what is x, what is y, what is z. Well, y has to be 11 over 5. X has to be minus 23 over 5 plus z. But what is z? Well, z can be anything. Right? There's nothing left in this system of equations that says z has to be anything in particular. In fact, z can be anything as long as x is minus 23 over 5 plus whatever you chose for z. So z can be anything at all. So what we get here is, right, every point here is a solution. So here we have infinitely many solutions. In fact, if you remember about parametrizing lines, you might recognize that this is just a line in 3-space that's parametrized by a parameter z. So what we found is a whole line's worth of solutions to this system of equations. In fact, that's what we sort of should have expected way back here when one of the equations disappeared and we got 0 over 0. Right? We started with a 3x3 system with 3 variables and 3 equations. And we've seen in the past that typically with 3 variables and 3 equations, you get a unique solution, usually. But for this particular system, one of those equations was actually redundant. So even though it looks like this system has 3 equations, kind of it only has 2, since the third one is redundant. And we know that if you have with 3 variables and 2 equations, it's normal to get a whole line worth of solutions. And indeed, that's what we found, a whole line worth of solutions. All right, so if you do get infinitely many solutions to a system of equations, you can, after you back substitute, you get a parametrization of all of your collection of solutions. Let's look at one more system of equations. How about this one? So let's see. I think maybe a good way to start, right? Normally we would want to, well, not always, but often it's nice to have 1 times x in this upper left-hand corner. But the only other equation that has x's has the same coefficient. So maybe instead of dividing this first equation by minus 3 immediately, maybe it would be easier just to take our third equation, third row, and subtract the first row, because that's going to make the arithmetic a little easier. So first equation doesn't change, minus 3x plus 3y plus 6z equals 12. Second equation doesn't change because we aren't, right? Our row operation doesn't involve the second equation. So 4y minus z equals minus 2. And then we are doing third row minus first row. So that leaves us with no x's. And then 7y minus 3y is 4y. 5z minus 6z is minus z. And then 11 minus 12 is minus 1. Okay. Now things look a little suspicious, but let's press onwards. So now we have 2 equations left with y's and z's. So we can use this second equation to eliminate the y's in the third equation. So we're going to take row 3 and subtract row 4. I'm sorry, row 2. First equation doesn't change, so minus 3x plus 3y plus 6z equals 12. Second equation doesn't change. 4y minus z equals minus 2. And then the third equation, let's see, 4y minus 4y, there are no y's, minus z minus negative z, there are no z's either, so the left-hand side is 0. And then negative 1 minus negative 2, that's positive 1. So now our system of equation looks like this. And for this system of equations, it's obvious that there are no solutions. Because if we had a solution, it would make 0 equal to 1. But it's impossible to make 0 equal to 1. So this system of equations has no solutions. There must be some sort of either 2 of these planes are parallel, or maybe the planes are maybe the planes intersect like this. Maybe they intersect pairwise along parallel lines. One of those 2 situations. So whether you have no solutions or infinitely many solutions or just one solution, doing row operations will always let you solve a system of linear equations. Now all of these examples that we've looked at are either 2 by 2 or 3 by 3, but in fact this technique of using row operations to sort of clear out the variables below, you use one variable to clear out all the variables below like this. This technique always works to solve any system of equations with any number of variables and any number of equations.